here we have the one equations, and setting up the diffraction, the displacement at here, that's give us a second equation. The third one is to set up the slope. So again, here we utilize is using the continuity conditions. And that means here at this point, that is the interface between the two ranges. The diffraction must be continuous. The slope must be continuous. If necessary, we can say the double derivative of the value here must be continuous. Okay, so here the last one is we simply using y prime at y at x equal to L over 4, then y prime equal to y prime, y2 prime. Okay, so that means that gives us the third equation. So the third equation, then you write it up here and using this one. So that means 3p divided by 8 L over 4 squared will be plus A1. Sorry, for the people you sitting in the back, you need to stand up a little bit. And this one will be equal to minus P over 8 L over 4 squared plus P L over 4 L over 4 plus A3. Okay, so we simply set up using the three equations, we can solve for those coefficients. And this is a textbook examples, so let me get the numbers down. And here we find A1. This calculation can be very involved, but we just take it. So once we have those coefficients, then that is the form. For example, diffraction, we can use this equation and this equation. And the second equation, this one, can be used to describe the slope. So for example, if you want to know the slope of the diffraction at anywhere, you can use this equation and these equations. And I believe this is the one of the typical problems, but we can try. And so the key step is we have to find the m first, okay, and then proceed all the calculations. Sometimes, any questions to this? So this is a very typical solution process, and for any kinds of the beam, as long as you can figure out the equations for describing m of x, you simply plug in the equation, the EI y double prime is equal to m. Okay. So if there's no questions, then let me proceed to the next topic. From this equation, EI y double prime equal to m over x. And that is our starting point, is we calculate the m over x first. And then we proceed the integrations. And then the third one is to apply the boundary conditions to solve for the integrations. Constant So that are the typical procedures. And here I want to give you the different approach, which sometimes will be convenient, is this. Sometimes we can utilize, we know that the dm dx equal to v, and dv dx equal to minus omega. Okay, we know that from the chapters of draw the shear and bending moment diagram, we have utilized the two equations. So which means, depends on the conditions, if sometimes you are given the distribution is instead of m but v or w, then we can try what is w. W is the, for example, if this is a beam, and say this is the distributed loading, and this is w of x. Okay, so here is the w is means the distributed loading. And you know that for this kind of loading, sometimes for some problem it won't have this distributed loading. So that's the reason I'm saying here sometimes if that information will be available, then we can take this route. So if we have sometimes if we are given those kind of informations, then we might be able to rewrite the original equations to fit into these convenient informations. So if we are given, then we can try is this ei d square y dx square. So that is our definition of the ei y double prime. And this one equal to m of x. We're starting from here, try to utilize the information is this. Look at here. So here I take the one more derivative of the equation. So that means ei. And here in notation is the 3 terms, or that equivalent to square the d cube dx will be equal to here, because we take the derivative on everything, so here is dm over dx, and here we plug into here. So if you are able to find this information, you might just starting from here. That'll be convenient. Or we derivative one more time. So if we have a given this one, then here is ei force derivative, so that by definition is d to the force. And this one, you can see this basically is dv dx, and that is minus omega. Okay, so really depends on what kind of the conditions. If we are given this one, it would be easy to calculate this one, we're starting from here. If that would be easy or convenient, starting, or we can find this one, then we're starting from here. Or otherwise, if we by hand we can have this information available right away, then we're starting from here. Okay. So here that is the thinking process. Then I can give you one example to see. So here, for example, here we have the cantilever beam is under omega, 0 is constant. So here the length is L, and this has the Young's modulus E, I moment inertia. So for this case, we to find the y of x, and here, for example, here we pick up the x is from here is y, here is x. Because here we are given we are given this one, so I feel this one, we're starting from here, will be more convenient because we don't need to go spend time to find out what is the function of the mx. So we're starting from here. So ei y to the fourth power starting from minus omega 0. So minus omega x. And here is omega x is constant, so minus omega 0. So here we simply need to do 4 times of the integrations. So the first time we do the integration on the both side. So here will be ei y. The fourth derivative after integration will reduce by 1 degree. So that one will be equal to this one to integrate with respect to x, omega x plus the first integration constant, let me call C1. And then we do the second times of derivative on the both side here. ei y, and here is the third derivative. After integration, we reduce by 1, so that becomes the second derivative. So this is minus omega and 2x squared plus C1x. Then we proceed to the third one. ei prime will be equal to 6 minus omega 0 cubed plus C1, 2x squared plus C2. I forgot the one integration constant here. So C2x and plus C3. And then the last one, ei y will be equal to 24 minus omega 0 x fourth plus 6 C1 x cubed plus C2 2x squared plus C3 x plus C4. So here we do the symbolic integrations, and now leaving us 1, 2, 3, 4, because here we have 4 derivative, we have proceeded 4 times of integrations. So therefore we have 4 integration constants. And now the issue is start for those integration constants. Okay, those integration constants, and again, derived from the boundary conditions. And here, the little bit different on the boundary conditions is this. And in this secondary approach, the new things you have to pick up in your learning is on how to apply the boundary conditions. And compared to our first approach here, we said that if you remember, our boundary conditions always involve is only deflection and slope. But here, for this one, we will involve more. And here is the link, is a hint provided to you. You can see for the last equation is regarding y. So that means in this equation, if we be able to implement all the calculation, then this equation should have the dimension in length. So that means this equation seems implied to us this is regarding the length or regarding the deflection. So the physical information embedded in this equation is about the deflection. And in a similar way, this equation is involving the prime, which means the derivative or slope. So that means this equation implies we might be able to extract some information about the slope. Look at this equation. This equation is EIY double prime. EIY double prime actually is equivalent to moment. So that means implying this equation provided us is the information about the bending moment. And in a similar way, this one EI3 double EI the triple prime. This one is regarding this information. So that means this equation will give us all the information about the shearing stress, the transverse loading. Sorry, V is transverse loading. Transverse loading. I'm writing up here that is the physical meaning of each equation that can represent. So those writing help us to extract the appropriate boundary conditions. we have to, here we have 1, 2, 3, 4, 4 integration constants. We have to extract 4 boundary conditions. Those ones can be from boundary conditions about the diffraction, boundary condition about the slope, boundary condition about the bending, boundary condition about the transverse loading. Okay, so before the previous examples, we only exercise how to pick up the boundary conditions for slope and diffraction. Using this example, I want to show you how to extract the boundary conditions based upon the boundary conditions involve bending and loading, transverse loading. Okay, so before I doing that one, I need to give you a list. I summarize a few kinds of the boundary conditions here, and hopefully this can help you. So here in these tables, I use those notations. The capital delta means diffractions, and M means bending, moment, and V means shearing or transverse loading. And theta, sorry, here the theta means the slope. Okay, so here we have the one is, say, if this is a structure, and here I only draw a portion, so here it's kind of the breaking lines. So here has the support here. So here this is, we call the roller at one end. And for this case, the boundary condition is this. At this support, the diffraction, the vertical diffraction equal to 0, the diffraction vertical displacement. And then because this is a roller, the roller that means is free, the things you can see. If the roller is sitting here, it only can constrain the vertical displacement, but that allows free to rotate. Free to rotate, that means there's no bending constraint. So for this case, the bending equal to 0. At this port, okay. The second one is a pin. Okay, so here again, I only drew the portion, so this is a pin. And here the same, we have the diffraction that constrains the vertical displacement, but this allowed to level, so that is no bending. The third one is the simply supported, and maybe in the middle. The roller in between of two ends, so the same thing, this one has those boundary conditions here. And for the fourth one, we have the pin. In between, the same thing here. And now the fifth one is the clamp. So this is a fixed end. The fixed end, that means it fixes all the degree of freedoms, not only fix the translational, but the rotational degree of freedom has been fixed. So here we have is, at this end, at the support, no diffraction, and theta equal to 0. Okay, the slope won't be changed. And here you can see at the constraint here, they will induce the moment, so which means the moment won't be equal to 0, and etc. The sixth one, so this is called the free end. The free end could be something like this. If this is a cantilever beam, and say this is we call the free end.
Can you write that one a little higher?
This one?
Yeah.
Sure.